Section 7.7 is on base E and natural logarithms. E is an irrational number that's approximately equal to 2.71828 and so on. It's an irrational number, so it's a lot like pi. It continues on forever without ending. It's also referred to as the natural base. And this number appears a lot in science. It kind of shows up in real life situations. So it's another irrational number similar to pi that's very often used in math. The natural base function is f of x equals e to the x, and if the exponent is positive, it's exponential growth. If the exponent is negative, it's exponential decay. And its inverse is called a natural log, and we write that log base e of x, or ln of x, natural log of x. Here's a chart from your textbook. We're not actually going to graph these, but I thought it would be interesting to take a look at this. So this blue line on the left here is f of x equals e to the x, and you can see kind of some of the common points that we've had before. And if you reflect that over this green line, which is y equals x, then you get the natural log function. And that would be exponential growth with the base of e. This blue line over here on the right, e to the negative x is exponential decay, and flipped over the line y equals x, we have the opposite of the natural log function. So here's an example of how you use exponential and logarithmic forms with e. So e to the x equals y means that log base e of y equals x, or we abbreviate that ln y, natural log of y, is equal to x. Since e and the natural log function are inverses of each other, e raised to the power of ln x is equal to x, and the natural log of e to the x is x. And just a few other little formulas you should be aware of. Of course, e to the 0, anything to the 0 is equal to 1. E raised to the power of the natural log of 1 is 1. The natural log of 1 is 0, and the natural log of e is equal to 1. Let's take a look at a couple examples. Write each of these in logarithmic form. So here we have e to the 7th power equals x. So writing that in log form, it would be log base e of x equals 7, because e to the 7 is equal to x. But writing that in a little shorthand, we're going to say ln x equals 7, because log base e of x can be written ln x. Here's another example, e to the x equals 9. So that would be log base e of 9 is equal to x, or ln of 9 equals x. Let's take a look at these two here. Write each of these in exponential form. Oh wait, I wrote that wrong. Sorry about that. That shouldn't be logarithmic. That should be exponential form, because they're already in logarithmic form. Okay, natural log of x is approximately equal to 2.1438. Writing that in exponential form would be x is approximately equal to e raised to the power of 2.1438. And the natural log of 18 is equal to x would be e to the x is equal to 18. If it's a little hard to understand this ln thing, you can always write ln x as log base e of x, and then maybe it'll look a little easier to put it into one form or the other. Here's another example. Write 4 times the natural log of 3 plus the natural log of 6 as a single log, and we're going to use the properties of logarithms that we learned a couple sections ago. So this is actually going to be equal to, so 4 ln 3 plus ln 6, I probably shouldn't be saying ln, but natural log of 6, is equal to, remember I can take this coefficient and make that an exponent, the natural log of 3 to the 4th power plus the natural log of 6. And because I'm adding those two, I can say that this is equal to the natural log of 3 to the 4th times 6, which is equal to the natural log of 486. 3 to the 4th times 6 is 486. So that's what they mean by write it as a single log. So equations and inequalities can be solved by taking the natural log of each side of an equation or inequality, or by making each side the exponent of e. A lot like we did with common logs, we can also do that with natural logs and with e. So here's several examples. Solve each equation or inequality. So we have 3 times e raised to the power of negative 2x plus 4 equals 10. So I'm solving for x, so I'm trying to get x by itself. So the first thing I'll do is subtract 4 from each side. So that'll give me 3 times e to the negative 2x is equal to 6. And then I'll divide both sides by 3. That gives me e to the negative 2x equals 2. And now what I'll do is take the natural log of each side of this equation. So the natural log of e to the negative 2x equals the natural log of 2. And remember, the natural log of e raised to any power is equal to just that power. So that's negative 2x is equal to the natural log of 2. And solving for x, dividing both sides by negative 2, the natural log of 2 divided by negative 2, and plugging that into your calculator, that's approximately equal to negative 0.3466. And again, for most of these, we're going to be rounding to 4 decimal places. Here's another example. 2 times the natural log of 5x equals 6. First thing I want to do is divide both sides by 2. So the natural log of 5x is equal to 3. Now I will make each side of this equation the exponent of e. So e raised to the power of the natural log of 5x is equal to e to the third power. Now remember, e to the third power, e is not a variable, e is a number. So e raised to the third power is just a number. Okay, and then if you refer back to the rules that we looked at earlier, e raised to the power of the natural log of something is just whatever that is. So 5x equals e to the third power. And dividing both sides by 5, x is equal to e to the third divided by 5, which is approximately equal to 4.0171. And the last example in this category is an inequality. So the natural log of the quantity 3x plus 1 squared is greater than 8. So I don't like this squared, so I'm going to use my properties of properties of logarithms that say I can take an exponent and move it in front so it looks like a coefficient. So 2 times the natural log of 3x plus 1 is greater than 8. I can divide both sides by 2. So the natural log of 3x plus 1 is greater than 4. And now I'm going to make each side of this inequality a power of e. So e to the natural log of 3x plus 1 is greater than e to the fourth power. And as we saw in the last example, e raised to the power of natural log is just whatever that exponent is, or just whatever you're taking the natural log of, is greater than e to the fourth. And now we just need to solve this for x. So we'll subtract 1 from each side. And I will divide both sides by 3. So x is greater than e to the fourth minus 1 over 3. And plugging that into your calculator, we get x is greater than 17.8661. When you put that in your calculator, I'd use a lot of parentheses just to make sure you have it right, or do one step at a time. So a couple sections ago we had compound interest, but the compounding periods were at different times. There's another formula that we're going to take a look at here called continuously compounded interest. So in other words, the interest on the principal is compounded in a continuous manner. And the formula for that is A equals P times e to the power of r times t, where p is the principal, or the amount invested, r is the interest rate, expressed as a decimal, and a is the amount of money in the account after t number of years. So let's take a look at an example here. If you invest $700 at 3% interest compounded continuously, how much would you have after 8 years? So let's write our formula. A equals P times E to the RT. And let's identify what we have. So how much would we have? So that's what we don't know. Our principal is 700. My rate is 3%, and written as a decimal it's that, and my time is 8 years. So we just plug these numbers in. So A equals 700 times E to the 0.03 times 8 power. And plugging that into your calculator, you'll get that that is approximately equal to $889.87. So a lot simpler than the previous interest formula that we used. Let's take this a step further. So how long will it take until the account balance is at least $1,200? Okay, so I want it to have at least $1,200 in my account. So I'll write 1,200 because that's kind of the minimum I want to have, is less than 700, which is my principal, times e raised to the 0.03 t. Okay, so let's take a look at that. So it says how long will it take? So what I don't know is the time, the years, so that's why t is my variable. My interest rate stays the same, 0.03. My principal stays the same, 700, but I want this amount here to be greater than 1,200. I want 1,200 to be the minimum amount in my account. So I'm going to divide both sides by 700. So that's going to leave me 12 over 7 is less than e to the 0.03t. Okay, and since I have e raised to a power, I'm going to take the natural log of each side. So the natural log of 12 over 7 is greater than the natural log of e to the 0.03t. Taking the natural log of e leaves me with just the exponent. And here I have the natural log of 12 over 7. And then dividing both sides by 0.03, I will have that t is greater than the natural log of 12 over 7 divided by 0.03. Again, use lots of parentheses in your calculator or just do it one step at a time, or t is greater than 18 years. Oops, sorry about that. So it'll take at least 18 years with that principal deposited at that interest rate in order to get $1,200. And the last question is kind of related to that. How much would have to be deposited to have a balance of at least of $1,500 after 12 years? So after 12 years, I need to have $1,500 in that account and the interest rate remains the same. So my balance is going to be $1,500. I don't know what my principal is. That's what I'm trying to find. How much do I have to deposit? And then e to the 0.3 times 12. So my interest rate remains the same, but I want 12 years. So that's going to be 1,500 is equal to p times e to the 0.36. And actually, to solve this, it's very easy. We're just going to divide each side by e to the 0.36. So p is equal to 1,500 divided by e to the 0.36 power, which is approximately $1,046.51. So that's how much I would have to deposit to have a balance of $1,500 after 12 years. So in this section, we learned about the natural base e, and natural logarithms and how to use those to solve problems.